Lesson 9. Drive mechanism. Contents. The topics covered in this lesson are: types of motion, rectangular and polar coordinate systems, different types of wheels, different types of driving mechanisms, theoretical concepts of differential drive. The tasks and/or activities for this lesson include programming tasks for maneuvering the VEX Clawbot. Types of motion. There are different kinds of motion. The motion of an object in a straight line is called linear motion, for example, a train moving on a straight track. It is further classified into uniform and non-uniform linear motion, based on whether or not the velocity of the object is constant. Oscillatory motion is where an object moves back and forth in a repetitive manner, for example, the motion of a piston in an engine cylinder. Periodic motion is where an object passes through a certain point at a regular time interval, for example, a pendulum passing through its equilibrium position. Random motion is where an object moves in a random manner, for example, the random motion of water molecules when heat is applied. Note: higher the temperature, higher the amount of motion. Linear motion. The motion of an object along a straight line is called linear motion. It can be horizontal, vertical or neither, as long as it is in a straight line. There are two subcategories of linear motion: 1. Uniform linear motion. 2. Non-uniform linear motion. An example of vertical linear motion would be throwing a ball straight up in the air. It can be observed that the velocity of the ball decreases as it goes upwards and increases while coming back downwards. This is due to the acceleration caused by gravity, which changes the velocity during motion. It is an example of non-uniform linear motion. Uniform linear motion. In uniform linear motion, the same distance is covered in every time interval, that is, the speed is constant. For example, a person walking at a constant speed, that is, same number of steps in every time interval. It can be observed from the position time plot that the change in position for the car after every time interval of 1 second is the same, that is, 10 meters. Note: for linear motion, distance and displacement are the same. This is because the shortest path between the start and end points, a straight line, is the displacement, which is the same as distance for motion in a straight line. Consequently, the magnitude of the velocity is the same as speed. It can also be observed from the velocity time plot that the velocity remains the same throughout, 10 meters per second. Non-uniform linear motion. In non-uniform linear motion, the distance covered in time interval is not the same, that is, the speed either increases, object accelerates, or decreases, object decelerates. For example, a person walking faster as the time passes. It can be observed from the position time plot that the change in position is different for each time interval: 2.5 meters for the first second, 3.5 meters in the next second, and 4.5 meters in the last second. It can also be observed from the velocity time plot that the velocity increases constantly, accelerating at 1 meter per second square. Non-uniform linear motion. In non-uniform linear motion, the distance covered in every time interval is not the same, that is, the speed either increases, object accelerates, or decreases, object decelerates. For example, a person walking faster as the time passes. It can be observed from the position time plot that the change in position is different for each time interval: 2.5 meters for the first second, 3.5 meters in the next second, and 4.5 meters in the last second. It can also be observed from the velocity time plot that the velocity increases constantly, accelerating at 1 meter per second square. Oscillatory motion. Repetitive back-and-forth motion is called oscillatory motion. Common examples are motion of a piston in an engine cylinder, single-mass spring system, etc. In case of the mass spring system, after an initial disturbance, that is, stretching the spring by moving the mass attached to it, the restoring force, spring force, acts on the mass in a direction as opposite to the direction of stretch and towards the equilibrium position. If the mass is displaced in any direction from the equilibrium point, there is a growing restoring force, spring force, given by Hooke's law, F equals kx, acting to bring it back to the equilibrium point. This force acts on the mass in a direction opposite to the direction of spring stretch and towards the equilibrium position. The magnitude of the restoring force increases or decreases as it moves away from or approaches the equilibrium. Assuming no friction, there is no force acting at equilibrium, x equals 0, and hence no force acting against its motion, which causes an overshoot from the equilibrium position due to its inertia, and the restoring force starts to act to bring it back to equilibrium, resulting in an oscillatory motion. In reality, however, external forces like friction, air resistance, etc., that cause energy loss in the system during oscillation, causing the mass to slow down and stop after a while. Periodic motion. Any motion in which an object passes through a certain point at a regular time interval is called periodic motion. Common examples include the motion of the hands of a clock. The hour hand passes through each hour number once every 24 hours. Orbital motion of Moon around the Earth. Every 27 days, etc. Note that periodic motion may or may not be oscillatory, but oscillatory motion is always periodic. Random motion. Random motion is one in which the direction of motion changes in a random manner. The motion of a Roomba navigation autonomously in a room is a good example, although there are newer models that have advanced navigation methods resulting in motion that is less random. Kinematics. Kinematics is the branch of mechanics that describes the motion of objects without consideration of the forces that cause the motion. Please note that the branch of mechanics that is about the force analysis of motion is called dynamics. To describe the motion of an object, that is, visualize the displacement, velocity, etc., a frame of reference is required, the choice of which is arbitrary, but should remain the same throughout the motion analysis. A coordinate system is used for this purpose to specify the position of objects in space. Coordinate system. A Cartesian coordinate system is composed of baselines, often referred to as x-axis and y-axis, that intersect at right angles, and the point of intersection, 0, 0, is called origin, O. A location in 2D space, point, is specified using the linear distance of the location in the horizontal and vertical direction along these axes. For example, the location P in the figure has an x-coordinate of 2 units, that is, 2 units away from the origin in the x direction, and y-coordinate of 3 units, that is, 3 units away from the origin in the y direction, and is therefore P is specified as 2, 3. A polar coordinate system is composed of a combination of linear and angular units. A location in 2D space, point, is specified as a linear distance from the origin and an angle from a reference axis, usually counterclockwise from the positive x-axis. For example, the same location P, 2, 3, in polar coordinates can be specified as 3.6, 56.3 degrees. Polar coordinates to rectangular coordinates. Given polar coordinates r and theta, it can be converted to rectangular coordinates using the given formulae: x equals r times cos of theta and y equals r times sine of theta. Note that in Arduino IDE, trigonometric functions take angle input in radians. Converting polar coordinates to rectangular coordinates. Problem. If the location of a robot has polar coordinates, 4, 300 degrees, what are its Cartesian coordinates? Use the formulae and the diagram shown as reference to solve the problem. Pause the video here to attempt the problem and hit play when you are done. Solution. Given polar coordinates are 4 and 300 degrees. In Cartesian system, the x-coordinate will be 4 times cosine of 300 degrees, which equals 2, and the y-coordinate will be 4 times sine of 300 degrees, which equals minus 3.46. Therefore, the equivalent Cartesian coordinates are 2 and minus 3.46. Rectangular coordinates to polar coordinates. Given rectangular coordinates x and y, it can be converted to polar coordinates using the given formulae. By Pythagorean theorem, r squared equals x squared plus y squared. By trigonometry, theta equals the inverse of y by x. Converting rectangular coordinates to polar coordinates. Problem. If the location of a robot has rectangular coordinates, 3, 4, what are its polar coordinates? Use the formulae and the diagram shown as reference to solve the problem. Pause the video here to attempt the problem and hit play when you are done. Solution. Given Cartesian coordinates are 3 and 4. In polar coordinate system, r will be square root of the sum of 3 squared and 4 squared, which equals 5, and theta equals tan inverse of 4 by 3, which equals 53.1 degrees. Therefore, the equivalent polar coordinates are 5 and 53.1 degrees. Refresher. Arduino. Recall the structure of Arduino IDE, particularly the serial monitor. For the upcoming activity, the Arduino will be used for computing coordinate system conversion, and unlike other programs, since the output would require to be displayed in the serial monitor, the Arduino must remain connected to the computer. Programming. Serial.begin is the command that opens serial port and sets the boot rate for serial data transmission. Typical boot rate for communicating with PC is 9600, although other speeds are supported. When using serial communication, digital pins 0, RX, and 1, TX, cannot be used at the same time for other purposes. Serial.print is the command used to print data to the serial port as human-readable ASCII text. The string command constructs a string from the input data, which is usually of int, float type, which results in a string that contains the ASCII representation of that data. Activity 1. Write a program to display polar coordinates of robot if Cartesian coordinates of robot location are 5, 6. Pause the video here to do this activity and hit play when you are done. Activity 1. Solution. All the required variables are declared as float type. In the setup, serial communication is initiated at a set boot rate. The square root and arc-tangent function are used to calculate the values of r and theta, respectively. The rest of the program is just serial.print statements to display the polar coordinates. Since only string characters can be displayed in the serial monitor, the float values are converted to string using the string command before passing the values to the print command. Drivetrain. A robot's drivetrain consists of all the components used to make the robot move, that is, motors, wheels, and transmission. The wheels, gears used for transmission and the motors for the VEX Clawbot are shown as an example. X-wheel drive. X is the number of wheels that are connected to motors, that is, the number of wheels or motors a robot has does not matter. What matters is the number of wheels that are powered by the motors. For example, in a two-wheel drive, 2 wheels are powered. The robot can have 4 wheels or 6 wheels, and only one motor, but as long as only 2 wheels are connected to that one motor, it is called a two-wheel drive. The VEX Clawbot is an example of a 4-wheel drive since it is a 4-wheeled robot, in which all the 4 wheels are powered by the motors. Again, the number of motors does not matter. Chassis. These are the most common hobby robot chassis that are available in the market. The one on the left is a 2-wheel drive, although it has 3 wheels, only 2 are powered by the motors, and the one on the right is a 4-wheel drive since all 4 wheels are powered by motors. Wheels. There are 3 main types of wheels: fixed wheel, steerable wheel and caster wheel. A fixed wheel can rotate about the axis that goes through the center of the wheel and is orthogonal to the wheel plane. A steerable wheel has 2 axes of rotation. The first is same as the fixed wheel. The second is vertical and goes through the center of the wheel. A simple example is a bicycle, in which the front wheel is steerable using a handle, while the back wheel of the bicycle is a fixed wheel. The third major classification of wheels is the caster wheel. It has 2 axes of rotation. Vertical axis does not pass through the center of wheel, from which it is displaced by constant offset. Such an arrangement causes the wheel to swivel automatically, rapidly aligning with the direction of the motion of the chassis. This type of wheel is introduced to provide a supporting point for static balance without affecting the mobility of base. Office chairs are one of the most common applications of caster wheels. There are various other types of wheels, some of the popular ones being the omnidirectional wheel and the mecanum wheel. Omnidirectional wheel or Swedish wheel is similar to a normal wheel but has a number of passive rollers around its circumference and their rotational axes lie in the plane of the wheel. For a mecanum wheel, the axis of rotation of each roller is typically inclined by 450 with respect to the plane of the wheel. Swerve or crab drive. A swerve drive robot has the ability to rotate its wheels and requires 2 motors at each corner. Swerve or crab drive in action. Each wheel has 2 degrees of freedom. One to rotate about its own rotation axis and second about the vertical axis of the wheel. Mecanum drive. Mecanum drive is a type of omnidirectional drive system, where the mecanum wheels are set up in a traditional 4-wheel drive system. Mecanum drive in action. This video shows a VEX robot with custom-made mecanum wheels. Differential drive kinematics. 2 motors separately control wheels on both sides of the robot. Rotating both motors at same speed drives the robot forward or backward, and reversing the direction of motor rotation reverses the robot movement direction. Rotating one motor at lower speed than the other makes the robot turn on the side of lower speed. One of the major constraints of a differential drive is that the robot can move forwards and backwards easily but cannot move to the left or right without slipping, which makes parallel parking require a series of maneuvers, unlike the mecanum drive. L298N motor driver. The L298N is a high-current, high-voltage dual full-bridge driver motor driver IC. It can control 2 DC motors simultaneously and independently and can provide 2 amps per channel at a supply voltage range of 4.5 volts to 46 volts. Note that L298N is instead of the L293D because the latter has a limit of only 600 mA per channel, and the VEX 393 motor can draw up to 20% of its maximum stall current rating, which is 0.2 times 4.8 amps, which equals 0.96 amps, which is greater than the 600 mA output limit of the L293D but less than the 2 amps output limit of L298N. L298N motor driver, pins. The pin diagram for the L298N motor driver is shown on the left and tabulated on the right. Use this as a reference for interfacing the VEX 393 motors in the next activity. Caution. The VEX 393 motors draw very high current. Do not make circuit changes with the power supply connected. It is dangerous. Activity 2. Make the robot move forward at a specific speed. Please refer the worksheet from the link. Pause the video here to do this activity and hit play when you are done. Activity 2. Solution. Circuit. The circuit shown needs to be built for interfacing the VEX 393 motors with an Arduino Uno. Note that for the 7.2 volts DC power supply, a battery pack of 6 rechargeable 1.2 volts batteries can be used. Activity 2. Solution. Code. The pins for both the left and right motors are declared as variables with meaningful names, that is, the name of the pins to which they are connected on the motor driver. In the setup, first, all these pins are set as output. In the infinite loop, both the motor speeds are set to maximum using the maximum analog write argument of 255 and using digital write. The motors are set to run in opposite direction. Here, the right motor rotates in clockwise direction and the left motor rotates anti-clockwise. Activity 2. Demonstration. Changing the analog write argument, which has a range of 0 to 255, changes the speed at which the motors run. Recall the concept of PWM signal for better understanding. It can be seen from the demonstration videos that different arguments values lead to motors, and consequently the robot, running at different speeds. Finding arc length. The arc length, s, of a circle is the product of the radius, r, of the circle and the angle, theta, formed by the arc with the center of the circle. Note that for this formula, the angle, theta, must be in radians, and the formula for converting an angle from degrees to radians is shown. Using these two formulas, calculate the arc length for the diagram on the right. Pause the video here to solve this problem and hit play when you are done. Finding arc length. Solution. First, the radius in converted into centimeters. 1 inch is 2.54 centimeters, so 10 inches is 2.54 centimeters. This step is optional, it can be left in inches. But the angle must be converted to radians by multiplying the values in degrees with pi by 180. 150 degrees is 2.62 radians. Now using the arc length formula, radius times theta, that is, 25.4 times 2.62 gives 66.55 centimeters. Kinematic equations for mobile robot, differential drive. As you can see in the diagram, for a differential drive, the left wheel and the right wheel do not travel the same distance during a turn. Therefore, using the arc length formula for the previous slide, the arc length for the left wheel, right wheel and the midpoint of the wheel axis can be calculated as shown. The angle remains the same, but the radius varies as these 3 points are at different distances from ICC, the instantaneous center of curvature, about which the robot rotates. Kinematic equations for mobile robot, differential drive. Problem. Before diving into the derivation further, try to solve this problem where the base length of the robot and the angle by which it rotates are given as 6 inches and 30 degrees respectively. Calculate the distance traveled by left, internal, wheel. Pause the video here to solve this problem and hit play when you are done. Solution. Using the arc length formula, the radius for the arc length traveled by the left wheel is r minus d by 2, which comes out to be 27 inches. This radius times the angle in radians, 0.524 radians, gives the arc length as 14.12 inches. Recall the formulas for the distance traveled by the left wheel, right wheel, and midpoint of the wheel axis. For the robot to turn from an initial attitude to attitude theta, in time, t, assuming a constant turning rate of omega, the magnitude of wheel velocities are as shown, which is basically the arc length by time. This gives the linear velocities of the 3 points in terms of omega. Therefore, now if the angle theta, time to complete the run, t, radius, r, and base length, d, are known, VL and VR can be calculated here. The assumption is that inertia, friction, etc., are negligible and that VL and VR are achieved instantaneously. That is, no need to consider accelerating to VL and VR. On the other hand, if VR and VL are known, using the above manipulation of the formulas, the turning rate omega and the radius of turning of the midpoint of robot base can be calculated using the formulas derived here. Using the formulas derived in the previous slide, these are the different cases of the values of the turning rate and the turning radius of the robot. For the robot to go straight, turn left, turn right and to spin at one spot. Try to calculate these values on your own, for better understanding of the concept. Activity 3. Make the robot take a 90-degree turn. Please refer the worksheet from the link. Activity 3. Solution. Code. The pins for both the left and right motors are declared as variables with meaningful names, that is, the name of the pins to which they are connected on the motor driver. In the setup, first, all these pins are set as output. Since the objective is to turn 90 degrees just once, the rest of the program is in the setup as well. The right motor is shut off and the left motor is set to run at full speed, which will cause the robot to turn right. By trial and error, 1,600 milliseconds was found to be the right duration for a 90-degree turn. After which, the left motor is shut off as well. Activity 3. Solution. This is a demonstration video of performing a 90-degree turn on the VexClawBot. The circuit is same as Activity 2. The tasks and/or activities covered in this lesson are programming tasks for different maneuvers of the VexClawBot. Refer worksheet for experiments with differential drive mechanisms. Moving forward, backward, turning left or right, for turning changing speed, velocity and direction. Thank you.